All right, so this is the first lecture, and we're doing a lot of review, so it's going to be fast and quick and crazy, this first few units. But when we're starting off, my goal of this problem is just to shake off the cobwebs, get some chemistry cobwebs out of the brain. So looking at this problem, we are talking about density, and we're looking at the density of 4 different liquids in a graduated cylinder. And notice how the liquids are one on top of the other, okay? So we have to identify from the list of known substances what the identity of liquid 1 and 3 are. So let's start with liquid 1. We're going to have 2 options for liquid 1. Can anyone tell me what those 2 possibilities are? Okay, I heard someone say hexane, and then ethyl alcohol, also known as ethanol. My question to you is, which one could it be? So let's first talk about this phenomenon of liquids sitting on top of other liquids. What is not actually going on if this is happening? I'm looking for a specific idea here. What is not happening to these 2 liquids if one is on top of the other? They're not mixing. They're not what? Okay, I'm glad you said reacting. We don't want to use the term reacting because reacting insinuates a chemical change, right? When things mix, is that chemical or physical? That's just physical, okay? So things aren't mixing. When things don't mix, we say they're not what in each other? They're not, say it again. Okay, homogeneous is a solution, but to be a solution, they have to mix and be soluble. Exactly, they have to be soluble in each other. So if things aren't soluble in each other, let's talk about things that are. You learned about this last year. You learned about things that dissolved in other things, and there was kind of a rule. It was the Chem 1 rule we always use. What was the rule about solubility? What dissolves what? Okay, solutes dissolve in solvents. Okay, I'll give you that. Tell me about water. What do you know about water? Water is a universal solvent. Okay. Tell me about the molecule water. I know you know a lot about it. What? It's polar. Okay, the molecule is polar. So what things will dissolve in water? No? I know you all learned the terms like dissolves like, right? I know you guys learned that. So what dissolves in polar substances? Polar substances. So polar things dissolve in polar things, and nonpolar things dissolve in nonpolar things. So just the opposite's true. Polar stuff will not dissolve nonpolar stuff. This year in AP Chem, later on, you're going to learn why this is true, why nonpolar things won't dissolve in polar things. We'll learn that from an energy standpoint. With that being said, since this is water, someone told me what was water. Okay, what was the important part? I said it 3 times. Polar. Water's polar, right? Since water's polar, what does the substance below it and above it have to be for them not to dissolve in each other? Good. This has to be nonpolar, and this has to be nonpolar. So the next question is, okay, which one is going to be nonpolar, hexane or ethanol? I want you to just to think about real life experience here, even if you don't remember your functional groups. Ethanol is a type of what? Alcohol. I know you guys aren't 21, so I know you don't have experience with this. So this is what you might have heard somewhere. Somewhere someone mentioned something about things being 80 proof or 70 proof. What does that mean? That it's what? Has alcohol in it, but what does it mean about the alcohol? And what? Water. You're insinuating it's what? Mixing, right? It's a mixture. So that proves to you just from your daily life that alcohol can actually mix with water. So what does that tell you alcohol is? Polar. So does that fit the description of what we need? No. So what does this have to be? Hexane. We're going to talk more about organic molecules later, but I don't know if you all remember, alcohol had an OH functional group on it. That caused the molecule to be polar, right? Because the OH created an intermolecular force called hydrogen bonding. Y'all remember the intermolecular forces? London dispersion, dipole-dipole, hydrogen bonding. Okay, so this is why ethanol is polar. Hexane is a straight chain. It's got 6 carbons, and it's saturated with hydrogens. Okay, it's going to have an even distribution of electrons all around, and no dipole exists, therefore it's nonpolar. So that is not miscible. The word miscible means dissolving. That is not miscible with water. All right, let's talk about this next one. This next one you should be able to do with very little knowledge of intermolecular forces based on something even simpler. What are my 2 possibilities for liquid 3? Aluminum, okay, and bromine. Okay. Which one is it? I'm gonna ask, one of you will get it. I'm going to put it, this is where I pause. Lauren got that it was bromine, so that is correct. It is bromine. And why is it bromine? Because bromine is a liquid. Now, I'm not saying aluminum isn't a liquid. Aluminum can be a liquid, but under these conditions, which are what? At room temperature, aluminum's a solid. So it doesn't even work to say it's aluminum because it's supposed to be a liquid by definition. But bromine is also nonpolar because if you look at the molecule, it's just this diatomic nonpolar bond there, nonpolar molecule. Okay? All right. Am I going to test you on polarity right away? No. This is just to shake out the cobwebs. I do expect you to understand the concept of things that are more dense are going to be at the bottom and things that are less dense are going to be at the top and all that. But other than that, this is just to wake you up, welcome you back to chemistry. All right, let's move on to the next problem. Here's some precision and accuracy. Again, a bunch of review. Who wants to define precision versus accuracy for me? In English, we use them interchangeably, which is not the case. But who wants to go? You are Paige. Correct. Accuracy is how close you are to the accepted value. And what's precision? Anyone want to give me precision? I'm slow with the periodic table. Philip. How the repeatability, how close data is to each other. So I could get on a scale, and the scale say I weigh 25 pounds, and I can get on there 27,000 times and it say 25 pounds. That scale is precise, but is it accurate? No, not at all. Nowhere near accurate. So that's the difference. Okay, with that being said, which set of measurements here then are precise? B and C. Which set of measurements are accurate? C. Now, I could argue that maybe A is accurate. Maybe the average of A is in that bullseye. We don't know that for sure, but it's not going to be a good lab situation because that data would be scattered everywhere and you'd be like, what's going on? Something's wrong with my instrument. So you'd probably stop and abort that whole process. Which set is both? Precise and accurate? C. All right. Who wants to tell me the difference between an exact number and an inexact number? First period was all over this. I was very impressed. So let's see if you all can beat them on this. Exact number versus inexact. Uh-oh. Johnny. Okay, you can see it on the, that's close. Okay, you're really close, but the fact is the inexact number, anytime you do a measurement, it's inexact. But you saying you can see it, that's close to what I'm looking for. An exact number, Paige? What do you call that? When you go 1, 2, 3, 4. It's a counting number, all right? If you can quantify it with counting, that is going to be your exact numbers. Now there's also, and with an exact number, what can you tell me about significant digits? Is one person different than 1.0 people, which is different than 1.00 people? No. There are, were you going to say something? Perfect. Alex says there's an infinite number of significant digits for a counting number, which is true. Okay, so we don't take counting numbers into account when we're doing our math. All right? That's why we don't do fractions in chemistry. That's why I get mad. I'm like, don't use a fraction, because that's an infinite number of sig figs. Okay? In chemistry, unlike physics, so silly physics people aren't going to make you round to sig figs. It keeps us honest. It keeps us measuring and doing calcs as accurately as we can. We're not going to lie and say that that's 0.55 mils if we actually know it's 0.6. Okay? So that's the difference. This is an example in AP where I don't write everything down. All right? You guys are in a college class now. Jot down stuff that you need to know. I'll put down a lot, but I'm not going to write down everything. So in each case, indicate whether the results is exact or inexact. Number of faces, exact. Mass of 6 apples, inexact. Anytime you take a measurement, it's going to be inexact. And it's going to vary from instrument to instrument. And you're going to learn that in our measurement lab that we do next week. Number of seeds in an apple, exact. Who said inexact? Anytime you count orange shoes, they're not as bright as yesterday's. Yeah, I figured as much. Okay, now here's the deal. When we get to conversions, I don't want you using conversion factors, period, in any of your math, okay? But as far as, and this is where the textbook will contradict, and every textbook is going to come up with a different, this is going to be our rule. If you're converting within the same system, metric to metric, or American to American, you're going to go ahead and say that that's an exact number, okay, because it's built that way. But if we're going to go from metric to American or American to metric, those weren't built on each other, so we're going to say those aren't exact, because those are ultimately rounded. Those are going to be inexact. So number of feet in 1 mile. That is American to American, so that's exact. The number of liters in quarts, we're going from metric to American. Inexact. Inexact. Y'all got that? But at the end of the day, when we do sig figs, I only want you to use given numbers. I do not want you to use conversion factors. And I will often throw things just like that. I get very animated and I throw stuff. Okay, sig fig review. Very exciting. Aren't you excited to be reviewing sig figs? All right, we get out at 22 after. Calculations for sig figs. When we're multiplying or dividing two numbers, what do we round our final answer to? It is Jesse. The least number of sig figs. We round to the same number of sig figs that the one with the least number of sig figs has. So I'm just going to write least number sig figs. If we are adding or subtracting, what do we round to? Eileen. Correct. The least amount of decimal places. Least amount of decimal places. Okay. So looking at this first problem, and so one thing you'll learn about me through the course of the year is I'm lazy and I don't do calculations. So all of you will have calculators, and you're going to do the calcs and holler out answers, and we'll make sure we get a group answer, and we'll move on from there. So looking at this first, this is a subtraction, so we're going to round our final answer to how many whats? 3 decimal places. So let's go ahead and do that. Do the math, and someone holler out, and we'll have someone else double check it. Someone else will acknowledge that number. Rounded answer. Remember dead babies? No dead babies, okay? Don't forget that 0. 0.27274 or 47. There's the dyslexia coming out again. I'm not dyslexic. I think I might be, though. I think 74. All right. Okay, the next one we're going to round to what? 1 place past the decimal, 1 decimal place. And what is that? 105. If anyone disagrees, please tell me. Don't let me sit here and put this on video and it be wrong. I'd rather us fix it in class. All right. Here's multiplication. What are we going to round our final answer to? 2 sig figs. So what is that? 1.2. All right, and this next one? 3 what? 3 sig figs, and then a point what? He got it last period. I stumped them. They said 0.067. To be 3 sig figs, you need that trailing 0. Okay. So this is, again, one of those situations where you should be reviewing this, doing lots of homework practice. Okay. Here's the deal. For the sake of this unit, in this unit, when we're covering this, we're doing the required math and we're playing by the rules of significant digits. And you're going to round after every single step in a problem like this. If the problem's saying, determine the number of sig figs in the following mathematical equation, you're going to do it that way. You're going to do the subtraction, round it. Do the division, round it appropriately. Do the addition, round it appropriately. However, if this were a math problem later on down the road where you were taking the density of this experiment and adding something else, you'd round at the end, okay? Just like you did in every other problem probably last year. You probably forgot about the whole rounding after each math step once you left the learning of sig figs. And so that's what we're going to do. So keeping that in mind, let's take this one step at a time. The first thing I want to do is do the subtraction and round to the 3 decimal places required, which would be what? Point what? 0.060. Okay. So now we're going to divide this. And because this is 0.060, how many sig figs is this? 2 sig figs. So we're going to take these 2 sig figs divided by those 5 and round have our quotient as 2 sig figs. So what is that number? 0.00061. Now, her saying that way is actually helpful. A lot of times students will do this and say 6.1 times 10 to the negative 4. 1, 2, 3, yeah, negative 4. In order to do this problem, it has to be in this version because we're going to add it to the next one, right? And so this only has 1 decimal place here, but that's not in the right format. So I see students sometimes using this and rounding to 1 decimal place, which is not the case. This is actually 1, 2, 3, 4, a 5 decimal place number added to a 3 decimal place number. So we really need to have 3 decimal places in our final. You all with me on that? So let's go ahead and add those 2 and round to 3 decimal places. 2.09. Aren't we so glad we did all that work for a change of 1, what is that, thousandth of a number? So exciting. All right, so practice your homework problems on sig figs. All right, now we're going to do a density problem. Probably can't read it now under my stuff here. Can you see around me? The density of concentrated sulfuric acid is 1.84 grams per mil. Concentrated sulfuric acid is 95% pure. The problem is asking what volume of concentrated sulfuric acid contains 100 grams of pure sulfuric acid. So at the end of the day, we're going to do a little dimensional analysis here. Given 100 grams of pure sulfuric acid, we want to know how many mils we'd need to take out of the container to get that 100 grams. But we have an issue. Every mil of sulfuric acid does not have 1.84 grams in it. Why is that? It's only 95% pure. So how many grams are actually in every mil? What are y'all thinking? I know you're thinking the right thing. Someone just needs to say it out loud. Where'd you get 1.748? Correct. You guys went ahead and said, hey, if it's 1.84 originally, but it's only 95%, you did your little, 95% of, did your multiplication. That 1.84, is it 90? Yeah, it's 95. Gives me the actual density of just the sulfuric acid, not of the solution, because there's some water in there. And you found that there are 1.75 grams per mil. That's how much is actually in there. So that being said, how do I now figure out how many mils I need? This is just dimensional analysis. We need to find out how many mils you need to get this 100 grams. Remember what this means. This could be a conversion factor, that 1 mil is equal to 1.75 grams. How would I place that to figure out mils? 1.75 grams on the bottom, 1 mil up top. Grams cancel. Make this a 3 sig fig gram. Put like a dot there or a bar or something. I do not want to round to 1 sig fig. Okay, so how many mils do I need? 57.1. Now, don't convert to volume. I had some people try to do that. Does it ask you a specific unit? No. That's the one thing you need to prepare for the AP. I don't want you doing stuff that's not asked because you can end up making mistakes. If you got a problem and you just randomly decided to convert it to liters because you felt like it and you did that conversion wrong, you can't get max points. And so why do that? Why chance losing points because you did something just to be fancy? All right? So notice that this is just a problem about density. This is the difference between AP Chem and Chem 1. This really only tests your skills on density and conversion factors. Did you need any more knowledge than you've already pretty much had? No, but it's a step up in the thought process, right? Okay, and that's kind of the big difference. A lot of the stuff we're going to learn this year is the same. We're just ramping it up a notch, okay? Okay, so here's where our flipped classroom comes into play. The new and exciting educational concept that everyone's all about. You guys need to read your books. You guys need to do your homework problems and need to review classification of matter and all your physical and chemical changes. That's all in the textbook. Read the book, and there's a ton of problems for homework that you can work and check the answers and make sure. This is just classifying matter as your mixtures and pure substances. Your mixtures can be homogeneous or heterogeneous. Your substances are anything from the periodic table, either singly or put into compounds. Okay, so you need to work on that. There's an extra chart as well. Let me move this a little bit if I can. Where we get into physical and chemical changes. I need you to also focus on this because you guys have a lab next week on this. And it's kind of an inquiry-based lab where you're going to go in and, based on experimentation, figure out if something's chemical or physical, okay? All right, so that's something that you need to be working on. What I want you to do y'all recognize these? Tonight, as part of your homework, I want you to go over this page and the next page and look through them, classify them, and if you have any questions first thing tomorrow, ask me. I want you to determine if it's a mixture or a pure substance, category 1, category 2, elements or compounds, or could be both, and tell me what category 3 is, solid, liquid, gas, or combination. Being able to do things like this kind of cover the whole gamut of classification of matter and physical and chemical stuff, all right? Okay, now let's review some dimensional analysis. Do y'all remember dimensional analysis? You use it all the time. You're going to use it to death in physics. Determine the number of kilograms in 115 pounds. I'm not going to hold you guys responsible for knowing American conversions. I need you to know the basic metric conversions, your centi, kilo. Well, I should write down which ones you need to know. You need to know centi, kilo, milli. Do we need them to know mega? Probably not. Nano will be good for when we get to waves and wave theory. Micro. Does anybody remember micro? Guys, it's -6. Nano is -9. And then these, -2, 3. I don't know which one's negative. I don't know. It depends whether there's a negative or not in front of it based on whether you're going from the meter to the centi or the centi to the meter, that kind of thing. There's 100 centimeters in 1 meter, right? How many millimeters in a meter? 1,000. And then how many meters in a kilometer? 1,000, but how many kilometers in a meter? 0.001. That's where the whole negative thing comes from. Just milli and kilo are 3, centi is 2, micro is 6, and mega is actually 6 on the other end. It's the big 6. And then nano is to the -9th, a nanometer. So these you need to know. But as far as this American stuff, you don't. We're just using it for the sake of actually doing dimensional analysis problems. If we have 115 pounds and we're doing dimensional analysis, you start with your given, and you're going to round to the same number of sig figs in your given. So we're going to round to 3. Who knows the conversion between pounds and kilograms? 2.2 what? Pounds per kilogram. So what are we going to put on top? 1 kilogram and 2.2 pounds. So to 3 sig figs, what is that answer? 52.3 kilograms. Okay, the next one. The approximate volume of water contained in the oceans of the world is 3.3E8 cubic miles. 3.3 times 10 to the 8th cubic miles. Determine volume in cubic kilometers. All right, let's get the miles into the, let's not even go to feet. I know a lot of you want to go to feet first. I don't want to go to feet. What I want to do is I want to think about the track. If I run a mile, how many times do I go around the track? 4. We know that each track is how many meters? 400 meters, right? So how many meters in a mile? 1,600 meters. Now, if you want to go to feet, that would have been fine, but then you had to go to inches, and then you had to go from inches to centimeters, right? Okay, and so you could have done that. I just think this is faster. So can I cancel out this mile with the cubic mile? No, what do I have to do? Cube. So I'm going to cube this, but if I cube the bottom, I have to cube the top. That cubes the number and the units. I'm not going to, since you're in AP now, I'm not going to make you figure out 1,600 cubed and rewrite it. We're past that at this point. Well, you should be. If you're not, we need to talk. Now my miles cubed cancel, and I'm in meters cubed now. Is that what I'm looking for? I'm looking for kilometers. How do I get from meters to kilometers? 1,000 meters on the bottom to 1 kilometer. Can I cancel the cubic meters with those meters? Nope. So again, I have to cube it. So now plug it all in your calculator. The beauty of these calculators is you can just do to the third, to the third, to the third. 1.4 times 10 to the 9th cubic. Wait, what am I going toward? Kilometers. Here's the deal about, I know this is physics and they're gonna let you do it, and that's fine that you're doing it, but on the AP, it is not favored for you to write 1.4E9. Reason is the chemistry professors at the readings, I'm one of the graders, and all the high school teachers are there fighting for the students, and all the professors are there trying to kill y'all and make y'all lose points, and so we all kind of like balance each other out. But they're not a fan of that, of writing the E, because it's not a number. And it's true, E isn't a number. E is kind of a representation of an exponent. So it puts them in a bad mood, which then puts them in the situation where they're less apt to give you points. It's human nature, totally human nature. So let's play nice and let the professors like your work. So I want you to write times 10 to the 9th, not E to the 9th. If you do it, I won't count points off, but I will give you angry notes and ugly faces and sad faces and tears and all that kind of stuff on your papers. Okay? All right, questions about dimensional analysis. Do you see how we're doing multiple units in like one day? All right. I just kind of want to get to know this periodic table a little bit, talk about charges and the different parts. and then we will call it a day. We get out of here at 22 after. Okay, first thing I want to do is go through all the different groups. So looking at the first group, and I didn't even realize that it's written down for you. Last period, everyone was getting it so quickly, and now I see why, because it's right there. Anyway, these are the alkali metals, alkali earth metals. All of these dudes are transition metals, all this center stuff. All this stuff are intertransition metals or rare earth. Okay. Over here, this group right here, which is not listed, very important group. What's that called? The halogens. The halogens are super, super important because they're going to be your most reactive nonmetals. What are these? Noble gases. These right here, who remembers? Chalcogens. Good. Those are basically the parts. There is a zigzag line that exists, and we're not going to stress about it, but it's somewhere in this area, zigzag. What's that the separation between? Metals and nonmetals, and things on that line are metalloids. You're never asked on the AP which is a metal and which is a nonmetal. It's so beyond the scope of what we do, so beyond that kind of thing. So don't stress about it. But just know that that exists. What I really want to go over, which is important, are the oxidation numbers, or the common charges that these metals will be when they're ions, and what oxidation states those nonmetals will have in ionic compounds. So looking at group 1, these things right here, what charge will they have if they become ions? +1, oxidation state of 1. What about this next group? +2. Okay, when we get over here to like nitrogen and phosphorus, when they want to be nonmetals and they're in ionic compounds, what are those going to be? -3. We're going to have some other action going on down here. Okay, this metalloid and those metals will like to become positive charges, and we'll talk about that in a minute. Oxygen and sulfur, for the most part in this group, -2. All the halogens, -1. And then we're going to say, for now, no oxidation state. However, starting on level 3 and beyond, your halogens can react, but we won't worry about that just yet. Looking at a couple of the other ones that I want you to know by heart, aluminum is always what? +3, and it's a stair step. Zinc is +2, silver is +1, 3, 2, 1. Cadmium is also +2 because they are together. Zinc and cadmium are together. All right, those are the only univalent charges I need you to know. For those of you who took regular chem, you didn't have to memorize your multivalent ones. Those of you in pre-AP did. You have to know them. So if you came from regular chem, write these down, start memorizing them. Pre-AP, start remembering them. Iron, cobalt, nickel, what are those two charges? +2 and +3. Good. Gold. 1. Good. +1, +3. Copper and mercury are both very good. +1, +2. So Lincoln knows his charges. But let me ask you about mercury. Mercury is kind of weird. When mercury is +1, it's a what? Diatomic. Mercury can only be +1 if it's in a diatomic form. There's 2 of them, and each one is a +1. Okay. All right, now let's kind of scooch on over to some of these here. Lead and tin. When arsenic decides to be a metal and not a nonmetal, lead and tin are, it's kind of a pattern. Dun, 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 dun. 2, 4 here, 3, 5. That's pretty easy to remember. It's like a shift over, 2, 4, 3, 5. So you need to really start committing those to your brain. And doing this today is going to help us when we get to nomenclature tomorrow, okay? So kind of work on those. I think that's all I had planned for you. Oh, nope, we're going to do this too. We can do this real quick. This is easy. This is your notation, nuclear notation for different elements. And let's talk about what this notation means. What is that 47? Protons, also known as atomic number. Atomic number. What's the 107? Close. I'm gonna say no, and I'll tell you why in a minute. It's really mass number, which is protons plus neutrons. Can anyone tell me why I said no to atomic mass? Because you know what? Atomic mass is this. That's atomic mass, that's atomic mass, that's atomic mass. Perfect. The atomic mass is the average of all the different isotopes, okay? The mass number is the actual number of protons and neutrons in that particular isotope. So silver can have a 107, a 104, a 105, a 108, all these different kinds of isotopes. But here, its atomic mass is 107.8682. That's because this is the average of all the different kinds of silver. All right, do you see the difference? Okay, so I need you to know that difference. And then the charge right here is based on number of electrons. This atomic number does not change. If it changes, the identity changes. So if you're going to make something charged, you have to mess with the electrons and only the electrons. Okay? So two atoms are walking down the street, and one atom says to the other, hey, someone stole my electron. And the other atom's like, how do you know? Are you sure? And he's like, yeah, I'm positive. Get it? Get it? A neutron walks into a bar, asks the bartender, how much for a drink? The bartender says, for you, no charge. All right, you guys. He's too charged up to go into a bar. He's too negative. See, I'm quick. All right, so I'm just going to make a little chart here for all these different ones, and we'll do this real quick. So we're going to have protons, neutrons, and electrons. And we'll do all these real quick. This is the first piece that's really like exactly like this on the test. You're going to be given nuclear notation, and you're going to need to give us some stuff here. Give us some protons, neutrons, and electrons from it. All right. How many protons in the first one? 47. Neutrons? 62. And electrons? 47. There's no charge, so proton electrons has to be the same. Magnesium? 12. 12. 12. Aluminum? 13. 47. 60. We need one more proton than electron, so 46. We do not change the proton number. It changes the identity of the species. All right, so that's it for today. I will go ahead and pause this. I'll stop it.